In the last episode, we diligently toiled for these two chunker expressions right here, where these big boys locate the intersection of two normal lines from a parameter. Going back to where we left off, we now have to take the limit of these two chunkers as the variable b approaches a. In the visual context of this scenario, taking the limit as b approaches a allows the two normal lines to converge as to appear that the lines seemingly coincide. Since they are still not the same line, they still should intersect at some point. Yet, paradoxically, the two lines are so close that they can be treated as one line, and this merged line would still have an intersection point somewhere. This is the magic of taking the limits. You get lines intersecting themselves at a valid location. This one-line intersection point is the point we're looking for, called the center of curvature, or the COC. Since b approaches a, our COC expressions will basically be dependent on a instead of a and b, because the b line has merged with the a line. The limit is no big joke, as you have to add and subtract same equal terms, multiply and divide same equal terms, and execute trial and error to same equal terms. These are some strategies needed to take the limit of that expression on episode 6.9. Nice. But the thing is, taking the limit of the function form expressions in 6.9 are child's play compared to the parametric form expressions in this episode, which are way worse. Because of this, I shall be uploading a 60-minute video explaining how to take the limit of these chunker expressions. Kidding. I would rather live my life cheerfully than make an even longer video about limits. In God's name, no, I won't. Though I do admit, in God's name, that I had unlived my life despicably and did this limit myself in the past for like 12 hours with 3 to 4 attempts tops. I lived with that brain melter and I don't want to go back to that torture no more for a video. But, the least I can do for you is provide thee with the Desmos link of my successful attempt at taking the limit of these expressions. Spoiler alert, there are more than 40 steps of changing the expression and partial limit taking along the way, so good luck reading my trash. If I am subconsciously unwilling to take the limit of these expressions, how can? Well, there's actually a tenfold easier way to take the limit of these guys. But there's a disappointing repercussion. You see these expressions we found with hard work last episode? We don't need them. We don't need them and we won't use them. I guess in a way that's my April Fool's joke to y'all, but nope, we won't use them. So, in what godforsaken manner can I take the limit now that we just dumped these beautifully crafted expressions? Well, another way to take the limit of these expressions is by deriving from the function version of the center of curvature into a parametric form. By that I mean, what are these expressions but with xt and yt? How can we convert function to parameter? But before we do convert, there's actually a neater way of arranging these lengthy function expressions to a more compact and understandable version, which may help at converting. It goes like this: a f of a plus f prime a squared plus 1 over f prime prime a times negative f prime a 1. You can see how I formed this based on comparison to the separated function expressions. But what's better is that if you've watched my last video, then every gate in the world would have opened in front of your eyes. Naturally, what this conjoined expression means is that at some point, you start at the function's curve, as indicated by this first coordinate. Then, at that point, you face to a direction perpendicular to the function, indicated by the second coordinate. And then, at some distance, you walk to that perpendicular direction, where that distance is this overwhelming fraction right here. The second term might still be fuzzy to you, But in the context of this situation, it is more understandable to think of the first term as a position and then the second term as a quote-unquote vector, where you walk some displacement with a specific magnitude and direction. And to remind you, this entire thing here locates the COC of a function, and the COC is always some perpendicular distance from the curve if you haven't figured it out. With all this information unpacked, let's get on to converting this COC expression to parametric form. First term? Very simple. A f of a is simply just xa,ya, where xa,ya is just a point on a parameter. Now for second term. Let's work on the direction first, shall we? If negative f prime a1 is a direction perpendicular to the function, what is a direction perpendicular to the parameter? Here's a hint. Remember the slope expression of the normal line last episode? That slope is, of course, negative x prime a over y prime a. Now compare that to the normal slope of a function, which to remind you is negative 1 over f prime a. With these two slopes at hand, we can analogically come up with a direction perpendicular to the parameter, where this direction could be negative y prime a of x prime a. However, this is still confusing because negative y prime a on the x-coordinate and x prime a on the y-coordinate? As you may know truly, in the case of perpendicular directions, the rise and run get flipped over. To functions, 1 is the rise and negative f prime a is the run, and to parameters, x prime a is the rise and negative y prime a is the run. Let's move to the factor. Take a good look at this factor first. These f's are the main variables we'll be converting to parametric form. You might know what f prime might be in parameters if you've seen the second episode, where we interpret f prime as the rate of change of y as x changes. If f prime is a dy dx of a function, then a dy dx of a parameter is simply y prime over x prime. So in our factor, f prime a converts to y prime a over x prime a. This fraction here is the derivative of the parameter. But what about the second derivative? It's actually quite basic. You just take the derivative of this fraction with relative ease. Taking the derivative of a fraction requires quotient rule. And quotient rule is actually not basic. And now I have to correct myself that I first meant basic by the idea that you just have to take the derivative of the function and that I didn't mean the process of taking the derivative. Anyways, using quotient rule, we first write the then num derivative minus num then derivative all over then squared. Following that process yields x prime a, y prime a minus y prime a, x prime a all over x prime a squared. Replacing f prime prime with this whole thing, we get this nasty complex fraction. But you know what? We can organize this. The simple organizer is by multiplying both num and then by x prime a squared. Doing so gets rid of the x prime a squared on the lower denominator, gets rid of the x prime a squared under y prime a squared, and turns this numerator 1 to x prime a squared, ending up with this simpler fraction. And this simpler fraction, folks, is the factor of the second term. Out loud, our final expression as a whole is xa,ya plus x prime a squared plus y prime a squared all over x prime a, y prime a minus y prime a, x prime a times the coordinate negative y prime a, x prime a. This expression right here is the limit of the two chunk expressions joined into one. This limit taken expression, finally, is the center of curvature of a parameter, or the infinitesimal intersection of two lines across a curve. Although infinitesimal intersection allows two lines to merge into one, the merged line still intersects. Not intersects with, not intersects to, the line just intersects. In our particular scenario, every individual normal line intersects at this coordinate expression where its position is determined by the value of a. And if I let a run through different values, the point will dynamically move in a manner that, well, weirdly enough, I relate this point to those two contrasting Twitch emotes where Pepe arrives because something attracts his attention and then leaves because he then decided it's not worth his time, like this video. But this point's trajectory might be a bit clearer if I draw a normal line attached to this point. But it's still weird where this moving normal line intersects for values of a, because the intersection points have varying distances for the parameter. But what if we just trace the trajectory of this movement? What would it look like? Well, commonly we will see these things that may look like my visually artistic interpretation of a bird, a cuspy V-shape. I usually call them cone graph or maybe x and y parameter or some sort, but these terms have a more direct formal term. These cone graphs here are better called the evolutes. Evolutes, as you may infer, are simply the collection of all the centers of curvature of a curve. And the evolute of a parameter is mathematically the limit expression that we got, but with a generally considered general variable, like t. Honestly, it can still be a, but changing the t gives the association of something being more general. But nobody's gonna go bash you if you use, like, this weird trending internet symbol for the variable. Aside from having different variables, evolutes are basically the precise shapes formed from drawing the normal map of a parameter. And hey, imagine the varieties of normal maps or evolutes we can draw from the diversity of curves expressed by parameters. Imagine what the evolute of, let's say, a loop-de-loop or a trochoid is called, or a cycloid, or maybe even a spiral. Imagine what these shapes of these guys look like. But besides their cool shapes, there's something from either the map or evolute that we all strive for. And you know well what that thing is. And this is a good part to end the video. Thanks for watching.